So welcome to lecture 4D and 4C. We talked about acids, and now we're going to talk a little bit about bases, which are essentially the opposites of acids. So we talked about strong acids, and we can talk about strong bases. And we treat strong bases very much in the same way that we treat strong acids. As when we had strong acids, we talked about how they dissociate completely, and the same can be said for our strong bases as well. We see here we have sodium hydroxide, and we see again that single arrow that we had with the strong acids. And again, that strong arrow, single arrow indicates that we have just one reaction going in one direction, just towards the products. And what that means is that we have a conjugate acid and a conjugate base, and the sodium ion there is essentially ineffective as an acid, meaning it doesn't react with the hydroxide in order to go back and form NaOH. So remember, acids react with OH minus to give us water. So here we just have the sodium floating around. It doesn't really even think about the hydroxide there. So when you have our strong acids, we had ineffective conjugate bases. When we have our strong bases, we have ineffective conjugate acids. And that means that the conjugate acids and bases of strong bases and acids cannot drive that reaction in the reverse direction. And so the strong acids and bases only have their reaction go towards products, and they do not set up an equilibrium. So where do we find the strong bases? A good rule of thumb is they are group 1A hydroxide. So group 1A is your lithium, sodium, potassium, as well as most of the group 2A hydroxide. So calcium hydroxide, magnesium hydroxide, barium hydroxide. Those also serve as strong bases. Now, if we want to find the pH of a solution that was made from a strong base, we can find it fairly simply using the concentration of the base, but it does take a little bit more effort than it does with our strong acid, but not too much more. So we know that with a strong base, we have a complete dissociation. And so because we have that complete dissociation, that means that we can find the concentration of the OH minus ion, the hydroxide ion, using the original concentration of the base that we're given. So if we have a, say, 0.4 molar sodium hydroxide solution, I know that the hydroxide concentration will be 0.4 because we have that complete dissociation. So here's an example here. What's the hydroxide ion concentration for a 0.05 molar sodium hydroxide? It would be 0.05 molar because of that complete dissociation. And there we go. Now, the more complex situation are weak bases. So they do have an equilibrium situation very similar to that of the acids, except with acids, we had the acid losing an H plus to the water. Here we have the bases. Bases take H pluses, and so we have our weak base taking H pluses away from water. So we saw our ammonia example earlier. Here it is again. So we have the ammonia plus the water. The ammonia is acting as a weak base. It is going to take an H plus away from water to give us NH4 plus and OH minus. When an H plus is removed from water, you get a hydroxide. Weak bases also have their own equilibrium constant. We just call it Kb. It is still an equilibrium constant, which means it's still concentration of our products over the concentrations of our reactants. Again, we just put that little label on there, that little B, to indicate that it is a base dissociation where we have our base taking an H plus away from water. That's what that Kb specifically means, is where you have a weak base dissociating water. So we're taking that H plus away from water. So if we wanted to write the equilibrium constant expression here, or base ionization constant, same thing. We have our Kb. So we're going to have our OH here, our NH4 plus, and then our reactant NH3. And here's an example that will work out. And what is the pH of a 0.55 molar solution of NH3? Actually, I'll have you work that out, and I will post the solution to that on YouTube. So I think you'll find that bases and acids work very similarly with ice boxes when you're using a weak acid or a weak base. But give this one a shot, and if you have problems on any of the concepts on this one, let me know.